Greetings and welcome to the video for problem set number 3 of Chemistry 151. Like the other videos for the problem sets, this is a video that I don't recommend you watch from beginning to ending, but instead kind of move around. If you've tried the problems ahead of time, you can just go to the problems which you have found troubling, and hopefully I'll be able to give you some hints to get you unstuck. This is a really cool chapter. It's all about balancing equations. Students usually do pretty good about it, but we'll go through these examples and stuff in detail and let me know if you have any other questions. If this video doesn't answer all of your questions, you can absolutely reach out to me. Email mike.russell@mhcc.edu works really well. You can also talk to the LSC/Avid Center at Mount Hood. Their website is mhcc.edu/LSC, but you can also reach them above the library in the Mount Hood campus. So for all these reasons, you got ways to get assistance. So without further ado, let's get into the problem set, starting now. The first question of problem set number 3, what do the symbols in parentheses stand for in the following equations? And you can see that there's a variety of different symbols in the equations in little parentheses. There's an L, there's a G, there's an S, and there's an AQ. And those are the 4 symbols you're going to see a lot when you're talking about equations. And they refer to the states of matter. So solids are S, all right? So the PCl5 there in equation A, that would be a solid. L is liquid, so PCl3 has an L by it. Sometimes you'll see the L listed more like a cursive L, something like that. Sometimes it looks like an L, sometimes it looks like a 1, I know. But if it's in parentheses next to a chemical equation like that, then you know it's a state of matter. Now G stands for gas, so Cl2, one of the diatomics, is a gas. And the last equation has several AQs, and that stands for aqueous. So aqueous means dissolved in water. So for example, on B there, that NaCl, that means that's not NaCl, which is, by the way, table salt. Table salt, if you put it on French fries or something, is a solid. This is sodium chloride in water. So that's a water-based reaction right there, because there's several things that are AQ. So knowing this, you can go through the symbols. On A, of course, L is liquid, G is gas, and S is solid. And on B there, you've got 3 species which are aqueous, the NaCl, the AgNO3, and the very final NaNO3, but the AgCl is a solid. It's insoluble. You would see it as a solid if you placed it in water. For each of these balanced equations, indicate how many atoms of each element are present on the reactant and product sides of the chemical equation. Now, this is the whole idea behind having a balanced reaction. And balance just means that the atoms that go in are accounted for on the way back out. The relationships of the atoms to each other is probably going to change, and you're going to see that on all of these examples. But the atoms that go in equal the atoms that go out. One thing that I like to do, and I'll talk about in the lecture, I talked about in lecture, sometimes I put a line right through the middle of the equation, and I'll have on the line the atoms that are here. So for example, Al and O are the 2 types of atom in this reaction. And I count the atoms to the left of the line and the atoms to the right of the line. So to the left, you can see 4 aluminums, and 3 times O2, 2, that 2 there would be 6 oxygen. If this is a balanced reaction, the product side will have the same. And sure enough, 2 times 2, 4 aluminums, 2 times 3, 6 oxygens. So you can see here that everything is balanced out. Atoms on the left equal atoms on the right, and that's what we see. Now that's really sloppy. Sorry, I wrote all over it there. There we go. Now you can see it better. 4 aluminum and 6 oxygens on both sides. And for all of these, the reactions should be the same on both sides. The second one, if you count up, there's 2 sodiums on both sides, there are 4 hydrogens on both sides, and there's 2 oxygens. Now the hydrogens on the product side, which is the right side of the arrow, are a little confusing at first maybe. The big 2, the coefficient, means 2 NAs, 2 Os, and 2 H's. So 2 H's from NaOH plus another H2 right there, you've got 4 hydrogens on that side as well. The next reaction, C, has cobalt, CO, it has mercury, Hg, and it has chlorine, Cl. And again, if everything is balanced, they should be the same, and sure enough, they are. You've got 2 cobalts on the left and the right, you've got 3 mercuries on the left and the right, and if you look carefully, there are 6 chlorines. There's 3 times 2 for the HgCl2, and there's also 2 times 3 for the COCl3. And then the last one, same kind of thing. You want to make sure everything's balanced. This last one does have a polyatomic ion on both the reactant and product sides. And it makes your life a lot easier if you balance reactions, keeping the polyatomics together. So because sulfate, SO4 minus 2, is on both sides, I would keep that the same. Keeps you from having to count endless sulfurs and oxygens and stuff like that. Ammonium is also a polyatomic, but there's no ammonium on the reactant side. NH3 by itself is ammonia, and that's different, so I don't think I'd keep it that way. But either way, when you count them all up, whether you keep sulfates around or not, 8 hydrogens, 1 sulfur, 4 oxygens, and 2 nitrogens, both sides. You could also, of course, combine the S and the O's together and say you have 1 sulfate on both sides, and that would be fine too. So now we're going to start balancing equations, all right? And we need to make sure, just like on the last examples, that the oxygens and the irons are the same on both reactant and product sides, or whatever chemicals we have going in. We have to make sure they're the same. On these kind of reactions, please remember the diatomics. Have no fear of ice clear brew, and they're going to pop up along. Now, an example of where that's important is in the first one. O2 is oxygen. That is a diatomic. Have no fear of ice clear brew, or the O in Hunkelbrief. Either way, it's one of the 7, so it gets a 2 next to it. Now, iron, which is Fe right next to it, iron is not one of the diatomics. It's not one of the have no fear of ice clear brews. Fear is fluorine, by the way, not iron. So we would write iron just by itself. If the element is not one of those 7, you write it by itself. But iron 3 oxide, which is Fe2O3, that's combined. The diatomics are usually the funky ones when it comes to balancing. So you can see you've got 3 oxygens in the Fe2O3, but oxygen, the diatomic, has 2. So one thing I would certainly try is putting a 3 and a 2 by each one of those, because that would make your oxygens balance out. And iron, which is by itself, should be the easiest one to balance. So once the oxygens are balanced, you can see there's 2 Fe2O3, 2 times 2. It looks like that should be a 4. Go ahead and check yourself at the end, and sure enough, 4 irons plus 3 O2 makes 2 Fe2O3. The next one, B, is similar. You have a nitrogen, or thanks for playing, you have a sodium chlorate, NaClO3. Notice the 3 oxygens. It's going to sodium chloride, but it's also going to O2. And again, O2 and the O3 on the left probably have to be taken into account. So on that one, I would try to do the 2-3 thing we did last time. I'd put a 2 by the NaCl3 to get 2 times 3, 6 oxygens, and I would put a 3 by the O2 to get 6 oxygens from that. And then NaCl, which is 1 to 1 in both NaCl3 and NaCl, would follow. So if you do that, that works out really nicely. If you put a 2 by the NaCl, you can then definitely see that everything is balanced. And by the way, I should have said this in the last one. If you ever get to the point where you're uncertain about one of these, do the little trick where you draw a line through the middle of what you think is the balanced reaction and just figure out how many atoms are on both sides. On the reactant side of A, you've got 4 irons and 3 times 2, 6 oxygens, like we talked about. And the product side, 2 times 2, 4 irons and 6 oxygens as well. You can do this on every one that you want to. It's not a problem at all. The next one, we've got gold 3 sulfide, Au2O. Au2S3, and it's reacting with hydrogen to make H2S and gold itself. All right, and this is one of the ones you just have to kind of start playing with. The sulfurs definitely scream to me that something has to be done there. So because the gold 3 sulfide, Au2S3, has 3 sulfurs, I would start by putting a 3 in front of the H2S, and you can go from there. If you do that, this is what you end up with: a balanced reaction. Au2S3 plus 3H2 makes 3H2S plus 2Au. And you are welcome to double check that. I have no problems with it at all. I do that myself quite a bit. Then the last one is ammonia reacting with oxygen. It makes dinitrogen monoxide, N2O, and water. And again, this is a little bit more complicated kind of thing, but you can probably see that the nitrogens aren't balanced, the hydrogens aren't balanced. I would try and balance oxygen last on this one, and I'm doing that last because oxygen is in both N2O and H2O, so if you change one of those, it would change oxygen. Try to do the O2 last. But either way, what I finally ended up with on this one was 2 ammonia, and that's going to give 2 nitrogen to balance the 1 N2O on the other side. When you do that, you're going to have 3 waters to make the hydrogen balanced, and then finally at the end, balance the oxygen. You've got 3 oxygens from the water and 1 oxygen from the N2O, so that means you need 4 oxygen atoms on the reactant sides, 2 O2. The more you practice this, the easier it gets. It's not hard, it just takes a little practice. You got this. More reactions. Now, this one, all of these are examples of combustion reactions. And in a combustion reaction, which is one of the types of reactions we're going to talk about, you start with something organic. It reacts with O2, and combustion means burn. So you're essentially burning the C2H4. When you burn something, you need oxygen. And the only products of a combustion reaction will be CO2 and water. Now, what I would do to balance this is I would balance carbon and hydrogen first and oxygen last, kind of like in that last example. So for C2H4, all of the carbon ends up as CO2. You're going to have a 2 right there, and that's because of the 2 in the formula C2. Likewise, hydrogen ends up as water. Water has 2 hydrogens, and we've got 4 total. So let's try putting a 2 right there. And at this point now, the carbon and the hydrogen are balanced on both sides, but oxygen we haven't played with yet. We're going to do oxygen last because oxygen is in both CO2 and water. So for CO2, 2 times 2, 4 oxygens, plus another 2 times 1, 2 oxygens for water. That's 6 oxygens total. O2 comes in pairs. 3 times 2 would be 6. That looks like it's pretty good balanced. So let's check this out. Sure enough, C2H4 plus 3O2 makes 2CO2 plus 2 water. That's kind of what I would do on all of these. All right, I would start by trying to balance the carbon and the hydrogen, and those are all the carbon goes to CO2, all the hydrogen goes to water, and then finally go to oxygen at the end. For the next one, C6, put a 6 right there. H12, hydrogen is in 2 in water, so we'd put a 6 right there. 6 times 2 for CO2 would be 12, plus another 6 for water is 18 oxygens. Oxygen comes in pairs. Let's try a 9 right there. Looking pretty good. So you can see how this works. And again, if you get stuck, definitely go back and try and balance it, making sure the atoms on both sides are balanced. Now, the next one we've got to be a little tricky. Next 2, actually, because oxygen is part of the organic part. And this happens a lot in organic chemistry. Oxygen is often part of the reactant. And that can be both a good or a bad thing, kind of depends on the problem. So for this one, start again, carbon to CO2, so start with a 3. And hydrogen to water. Water has 2, so let's try putting a 3 right there. Be careful of the oxygens here because, like we talked about, there's one in that reactant. So on the product right-hand side, we have 3 times 2, 6 oxygens from the CO2 plus 3 from the water. So on the reactant side, we have to have 9 oxygens as well. One of them is in the C3H6O. That means we have 8 left over. Let's try putting a 4 right there. And if you do that, sure enough, lo and behold, that's the reaction you want. The last one, same kind of thing. Let's do the same kind of steps. Remember, you've got O2 in the reactant. So C5 means we're going to need 5 CO2s. H10 in hot water has 2, means we're going to have 5. Let's count up the number of oxygens on the reactant side. So 5 times 2 plus 5, 15 oxygens. And you might be seeing a problem, but I'll talk about that in a little bit. So if there's 15 oxygens on this side, and you really don't want to change reactant stoichiometry, that means oxygen, we would want to have 13 oxygen atoms, but the diatomics come in pairs. So what we would like to do here is have 13 halves O2. Now, this is a little weird at first, but 13 halves oxygen, and there are 2 oxygen atoms per O2, that would give us our 13 oxygen atoms. So one version of this reaction, which I think would be balanced, would be C5H10O2 plus 13 halves, which by the way is 6.5 O2, and that goes to 5 CO2s and 5 waters. But I'll tell you, chemists really do not like using fractions, and 13 halves, 6.5, is certainly a fraction. So instead of doing that, what chemists like to do is multiply the entire thing by 2. So you'd have 2 C5H10O2, and you'd have 13 halves times 2, or 13 O2s, making 10 CO2s and 10 waters. And that's what you would do here to solve it. But wait, Dr. Russell, isn't the oxygen weird? Good question, whoever asked that in the back of the room in the invisible virtual world I can't see. Anyway, seriously, remember, anytime you want to check these out, balance them. Make sure they're balanced. So on the reactant side, we've got 2 of those weird organic things. That's 2 times 5, that's 10 carbon, and 2 times 10, 20 hydrogen, and 2 times 2, 4 oxygen, plus 13 times 2, 26. That's 30 oxygens total. I listed them like that separately because if we have to go back and fine-tune anything, you can, but it's up to you the way you want to do it. Now, if we've done this right, the product side will have the same. So 10 CO2s would be 10 carbons. Good, that's balanced. 10 times 2, 20 oxygens, but we still got water. 10 times 2, 20 hydrogens, so that's balanced, plus 10 times 1, 10 oxygens. And sure enough, carbon's balanced, hydrogen's balanced, oxygen's balanced. Cool for school. But again, never be afraid to go back and check that. That's not a problem at all. And I do it myself quite frequently. Probably more than I should, but that's another story. Let's balance these reactions, which are a combination of different types we'll see, especially in the lab. The first one, aluminum and tin 2 nitrate, which is what that compound is making aluminum nitrate plus tin. Aluminum is one of the stairs, so it doesn't need a Roman numeral, but tin certainly needs a Roman numeral next to it. This is a good time to pay attention to your polyatomic ions, because the polyatomic ions can be thought of as units on each side. So for example, in this problem, you can see there's 2 nitrates with the tin and 3 nitrates with the aluminum. So we've got to change those numbers around. Let's try the trick we did with oxygen earlier. Let's do a 3 there and a 2 there. And that would at least make the nitrates on both sides. So again, notice I'm not counting nitrogens and oxygens. I'm counting the whole nitrate thing here, and that'll make your life easier. Also, because aluminum and tin are by themselves, you can just balance out those pretty easy. So on the right side, the product side, we had to put a 2 in front of the aluminum nitrate to make the nitrates balanced. We'll put a 2 in front of the aluminum. It'll be balanced too. 3 tins are now on the reactant side, so let's try putting a 3 right there. And if all is said and done, came out really nicely. Very cool. The next one, we'll do the same kind of thing. On B, this is actually an example of what's called a precipitation reaction, but we'll talk about that later. This is kind of a cool reaction because carbonate is on both sides and nitrate is on both sides. And again, to make your life easier, don't break those up. Keep them as nitrate and keep them as carbonate. And you can probably see right away that, wait a minute, 2 nitrates on the reactant side, only 1 nitrate on the product side. There's also 2 sodiums on the reactant side and only 1 on the right. So let's try putting a 2 right there. If you do that, everything is balanced. Life looks good. The precipitate in this reaction is MgCO3. Now it doesn't state that and you don't need to know it, but if you're curious, that's the insoluble compound. And in the Chem 200 level, we'll actually see that compound being made. The next example also has polyatomic ions. There's the sulfate ion on both sides, and there's the nitrate ion on both sides. So this one, the aluminum sulfate on the product side, has a lot of sulfates. So we've got to take that out. Let's put a 3 right there. That will at least make the sulfates okay. And you can see that there's 2 aluminums in aluminum sulfate, so we're going to have at least a 2 right there. Now, by putting a 2 in front of aluminum nitrate, you then have 2 times 3, 6 nitrates. You're going to need 6 HNO3. And that's good because in the sulfuric acid here, we had 3 times 2 or 6 hydrogens as well. So this reaction, 2 aluminum nitrates plus 3 sulfuric acids, makes aluminum sulfate plus 6 HNO3. The last reaction here has many polyatomic ions in it. The first compound is called barium acetate. Acetate is C2H3O2 negative 1. Barium, a main group metal in group 2A, needs 2 negative 1 acetates to balance it. It's reacting with ammonium phosphate, which has both ammonium and phosphate in it. On the product side, you have barium phosphate, and also this other thing, which is really long and looks weird. It doesn't look as weird if you split it like that. It's an ammonium with an acetate, so that compound is ammonium acetate. So like before, keep the polyatomics together. Let's deal with the phosphates first. The product side, barium phosphate, has 2 phosphates, so we're going to have a 2 right there. Also, the barium phosphate has 3 bariums, so you're going to have a 3 right there. Now, 3 barium acetates on the reactant need 3 times 2, 6 acetates on the right. So let's tentatively put a 6 right there. That's good because the 2 we put there times 3 would be 6. I believe that's balanced. Bam! 3 barium acetates plus 2 ammonium phosphates makes 1 barium phosphate plus 6 ammonium acetates. And again, I encourage you to balance these anytime you want. In this one, to balance it, I would have the barium. I would have the acetate ion, which is that thing, C2H3O2 minus 1. I would have ammonium, which is NH4, and I would have phosphate, which is negative 3. So on the reactant side, 3 of the barium acetates means 3 bariums, and 3 times 2, 6 acetates. And then the ammonium phosphate on the reactant side means 2 times 3, 6 ammoniums, and 2 times phosphate would be 2 phosphates. On the product side, barium phosphate has 3 bariums and 2 phosphates, so those look good. And 6 ammonium acetates means 6 ammoniums, and it means 6 acetates. So again, everything balanced, all is good. Law of conservation of matter is being followed. This makes your world a lot easier when you're thinking about things from a chemist's perspective. These reactions we're going to classify as precipitation, decomposition, single replacement, combustion, acid-base, base or combination reactions. All right, so those are the kind of possibilities that we're going to go through. So let's go through these and figure it out. The first one, copper sulfate, copper 2 sulfate, is reacting with aluminum. It makes aluminum sulfate and copper. And if you stare at this long enough, aluminum and copper are trading places. So aluminum starts dancing with sulfate, copper then dances by itself, if you will. And the charges have to be maintained. Aluminum is a +3 stere element, while copper is +2. That's where there's a difference. So the stoichiometry is strange. If one atom traded places with another, that means it's a single replacement reaction. The metals are trading places with the metals here to make the new products. In a single replacement, you can have metals replacing metals. You can also have nonmetals replacing nonmetals, but you wouldn't want to have a metal replacing a nonmetal. You must have like species. Second reaction is potassium carbonate, K2CO3. It's breaking down to potassium oxide and CO2. Notice that there's only one reactant on this one, K2CO3. That one bigger molecule is breaking down to 2 or more smaller molecules, in this case K2O and CO2. That's called a decomposition reaction. Decomposition reactions only have one reactant, so that makes them not too hard to find. That's a decomposition reaction. The next one is an example of elements trading places, but instead of one of them dancing by themselves, they're finding new partners. In this reaction, the silver and the potassium are trading places. So on the product side, you have a silver sulfate and potassium nitrate being formed. And you have to put the 2's there because sulfate's -2 and nitrate's -1, etc., etc. All of that is great. We would call this a double displacement or an exchange reaction. It's like two cation anions trading places with each other, like at a square dance or something. I don't know. But anyway, another hint though as to what's going on here. Notice how this compound, it says solid. It's an insoluble solid. An insoluble solid in chemistry is a precipitate. So this example is a precipitation reaction, all right? In a precipitation reaction, a solid has to form. It's also a solid that forms through the double displacement or exchange reaction. So for all those reasons, that's got to be a precipitate. On D, there's only one product. And on B, we saw that only one reactant means decomposition. If there's only one product, that means that 2 or more smaller pieces are combining to make a bigger piece. And that's what's happening here. SO3 is being formed from SO2 and oxygen. This is called a combination reaction. So decomposition has only one reactant. A combination reaction has only one product. So that's pretty chill. E, we have sulfuric acid and potassium hydroxide. Now, sulfuric acid is an acid. It gives up the H+. Potassium hydroxide is a base. A metal hydroxide, a metal with an OH- is a base. And this looks like an acid-base reaction. Water is always formed in an acid-base reaction, and you also end up with some kind of what's called a salt. And a salt here is just the product of an acid-base reaction. It's not like table salt or something. Anyway, acid plus base making water plus some kind of ionic salt, that's definitely an acid base. Notice again though, it's another one of these displacements like we saw up on C, where H+ and K+, which are similar, are trading places. H+ starts dancing with OH-, and that's water, so that's where that comes in. On the other hand, K+ starts dancing with sulfate to make that K2SO4 thing. And the last reaction is methane, CH4, reacting with oxygen to make CO2 and water. And we did some of these problems just a while ago. Something organic is reacting with oxygen, making just CO2 and water. That's a combustion reaction. The O2 here is being used to burn the CH4, no problem. Here's the power of these types of reactions, all right? It says predict the products of these different reactions and write a balanced reaction. reaction. So the first one is AlCl3, and it's going into two things. Each of the question marks is like a thing. And notice how it says decomposition reaction into the elements. Okay, so because aluminum chloride has just aluminum and chlorine, it must be aluminum chlorine that's being made. Now, remember again, have no fear of ice clear brew. Chlorine by itself is going to be Cl2, but aluminum is not one of the diatomics. It'll be just Al. So you've got to make sure the chlorine's balanced, all that kind of stuff. You'll end up with 2 AlCs, making 2 Als and 3 Cl2. And this is a decomposition reaction. Just make sure to watch for those diatomics. The next one is an acid-base reaction. And in an acid-base reaction, like we said on the previous problem, an acid and a base react to make water and some kind of salt. Now the water comes from the H and the OH, which start dancing together. So that's no problem. The quote-unquote salt is going to come from the sodium ion and the nitrate, like the leftovers, if you will, of this reaction. So in this reaction, you would write HNO3 plus NaOH makes water plus NaNO3. And again, that's an acid-base reaction. The next one is a single replacement. So that means that two like things are going to trade places with each other. So on C, the aluminum is definitely going to bump something out. But the question is, does it bump the nickel or does it bump the nitrate? And always like wants to bump like. So aluminum and nickel are both metals. So those are going to be the ones that are going to be flipping. You wouldn't want to have Al and Ni coming together. That wouldn't be a compound. Nitrate will start dancing, if you will, with aluminum, and nickel will be by itself. Now, aluminum in an ionic compound is one of the stairs, and aluminum is a +3. Nitrate is -1 all the time. So one of the products will be Al parentheses NO3 parentheses 3. 3 -1 nitrates to balance the aluminum +3. On the reactant side, though, you can see we have nickel 2 nitrate, a nickel +2 and 2 -1s. So you've got to get the nitrates to balance first, then you can go and balance the aluminum and the nickel. And if you do that, it's 2Al plus 3 NiNO3 2, and that makes 2Al NO3 3 plus 3 nickels. You don't want to start changing the relative numbers of nickels per metal. All right, you wouldn't want to change NiNO3 2 to NiNO3 3 or something like that. Likewise, you don't want to have AlNO3 3 represented as AlNO3 2. Aluminum is always +3. That's what one of the stair elements is, and we're not going to change the nickel to nickel +3 in this problem. Regardless, this is a single replacement, aluminum and nickel trading places with each other, all is well. The last one is a combination reaction, 2 or more pieces coming together to make one piece. And the one piece on the product side is going to be a mixture of beryllium and nitrogen. So if you look on the periodic table, beryllium is a group 2A metal, and all of those are +2. So when beryllium is with nitrogen, it's going to be a +2 charge. Nitrogen is group 5A, and the nonmetals, you take that 5, the group number, and you subtract 8. That means nitrogen is going to be -3. So when the beryllium and the nitrogen comes together, you've got to have an equal number of positives, negatives. You can see that 2 times 3 is 6. So 6 divided by 2, you're going to have 3 berylliums, and 6 divided by 3, you're going to have 2 nitrogens. And again, what we're figuring here is we're just determining the formula of the product. We're not dealing with balancing or anything. We're just balancing the charges on the ions when they combine with each other. So beryllium nitride is going to be a product. And from there, you can go back and balance the beryllium. The nitrogen, I think, is already balanced. So this reaction would be balanced at 3B plus N2, and that's going to make beryllium nitride combination reaction. These are all metal carbonates, and metal carbonates are infamous, if you will, for turning into a metal oxide and carbon dioxide. So let's figure out what the balanced chemical equation is going to be for each one of these doing that, all right? And it's not too difficult. You have the metal carbonate as the reactant, and the metal, whatever it is going to be connected to an oxygen on the product side plus CO2. So in 8A, the metal is beryllium, and beryllium is a positive 2 metal. It's in group 2A. So when it's in an oxide, and remember oxide is negative 2, BeO is going to be made. So the first one, we would literally write BeCO3, the reactant, and that goes to BeO plus CO2. And again, it's BeO because beryllium is positive 2 in group 2A, and oxygen, group 6 minus 8, oxygen's negative 2, so the neutral compound would be BeO. Pretty simple. The next one is lithium carbonate. So lithium is the metal. It's going to form a lithium oxide and a CO2. But lithium is in group 1A. Beryllium was in group 2A, but lithium's in group 1A. So it's going to take 2 positive 1 lithiums to balance a negative 2 oxide. So when lithium comes together with oxide, it won't be 1-to-1 like BeO. It's going to be Li2O. Oxygen, still negative 2, but lithium is positive 1, so you're going to need 2 of them. So when you balance this reaction out, it's lithium carbonate on the reactant side, but you're going to have lithium oxide, Li2O, as a product, plus CO2. C, zinc, is the metal. Zinc, when it forms a compound, is one of the stairs. It's always positive 2. And notice how in A, beryllium was also a positive 2, a different element, but the same charge. So when you find out how this thing all works out, the equation's going to look a lot like A. We're going to pull the beryllium out and put zinc right in. And that's because zinc is positive 2, just like beryllium is positive 2. You'll start seeing these patterns more and more in chemistry. And guess what? D, cesium carbonate. Cesium is plus 1 as a metal. It's group 1A, just like lithium is a group 1A positive 1 metal. So when you do these reactions out, you're still going to need 2 cesium plus 1s for every negative 2 oxygen, etc., etc. It's going to look a lot like B. Cesium 2 or CS2CO3, cesium carbonate, makes cesium oxide, CS2O, plus CO2. So use your knowledge of balancing equations and also the charges to figure out how this stuff works out. These reactions are all organic things, if you will, and we're going to burn them all. Burn! Anyway, getting too excited here. Combustion means burning, all right? So in a combustion reaction, you're going to take whichever one of these you're looking at, and you're going to add O2 to it, and CO2 and water will be the only products. And like we saw earlier, the carbon should go to CO2, the hydrogen should go to water. Try to balance the oxygen last. If you end up with needing like 13 oxygen atoms, and oxygen comes as a pair, you can use that 13 halves and then multiply by 2, or whatever way you want to do it. The first one is pretty simple. 5 carbons and C5H12 goes to 5 CO2. The 12 hydrogens in the organic piece goes to 6 waters. And when you balance the oxygen, you're going to need 16 oxygen atoms or 8 O2s because, again, oxygen is a diatomic. Second one, similar kind of thing, except C4 leads to 4 CO2s initially, and H6 leads to 3 waters initially. And when you count up the number of oxygens, you kind of need 11 oxygen atoms, but O2 comes in pairs. So instead of having 11 halves, 11 over 2, you can multiply everything through by 2, and that's what's happened here. Then you get rid of that pesky pesky 11 halves O2, and you end up with just 11. So the best answer here, 2 C4H6 plus 11 O2 makes 8 CO2 plus 6 waters. The next compound, C7H8, same kind of thing. Add some oxygen to it. Carbon goes to CO2, hydrogen goes to water. Balance the oxygens when all is done. C7H8 plus 9O2 makes 7 CO2 plus 4 waters. And the last one, again, same kind of thing. All the carbon goes to CO2, hydrogen goes to water. Figure out the number of oxygens. If you have that fraction, multiply through by 2. I think we multiply this one through by 2. Yes, we do. So initially, you need 25 oxygens, not O2s, 25 oxygen atoms, and oxygen comes as pairs. So you could initially write 25 over 2. That would be balanced, but it's ugly. Multiply through everything through by 2. 2C8H18 plus 25 O2s makes 16 CO2s plus 18 waters. I'm putting this equation up last for a reason. This is the balanced equation for the combustion of octane, which is the main ingredient usually of gasoline in a gas-powered vehicle. So if you used your gas-powered vehicle today, or if you even have one, this is the equation you used. All of the combustion reactions give off a lot of energy, and that energy can be used to move the pistons in your car and make your car move and stuff like that, which is great. Unfortunately, the CO2 that's being generated is a problem for our environment, and that's another lecture sometimes, but at least you can see kind of the reactions. All of these would be potential fuel ingredients for your gasoline-powered car. Octane has the most energy per gram, or it's one of the higher ones per gram. Anyway, that's why they use it. And it's a liquid. Liquids are easy to use. Here are some more chemical equations we're going to balance using a combustion reaction. These have an oxygen in the reactant, though, and you've got to remember to take that into account before you're done with the reaction. Again, pretty chill. The piece that's listed, you're going to add O2 to it, and you're going to end up with only CO2 and water as your products. The carbon in the organic piece goes to CO2. The hydrogen in the organic piece you're given goes to water. Try to do oxygen last. Again, because oxygen O2 is a diatomic, some of these you'll need to use the fraction and stuff and then multiply by 2. No problem. So the first one, C2H4O. Initially, you'd have 2 CO2s from the C2H4O2, that 2, and you'd have 2 waters, but the number of oxygens you need is weird. Remember that there's already oxygen in the reactant, so you have to multiply through everything through by 2, and this is the balanced reaction you get. The next one is not as bad, though. C5 means 5 CO2s, H10 means 5 waters, and there's already 1 oxygen in the reactant molecule. On the product side, you have 5 times 2, 10, plus 5 oxygens, 15 oxygens, but you've got 1, like I said, in the organic piece, so that means you need 14 oxygens from the O2. No problem. 7 O2s will knock that one out. The next one, C2H4O2, you'll add 2 O2s to it, making 2 CO2s and 2 waters. And the last one, C3H6O2, initially you need 7 oxygen atoms from the O2, remembering there's an O2 in the reactant. So you multiply through everything by 2. That's what you get. All the reaction is balanced. Here are 2 more reactions. These are a little bit more challenging. These don't follow the standard 6 types of reactions, so it's a little bit crazier in ways to figure out. The first one is ammonia, NH3. It reacts with oxygen and methane, CH4, to make HCN and water. And obviously there's a lot more pieces to this one. Try to keep the oxygen last is what I would recommend on the first one, and play with the hydrogens especially. Now, just like on the combustion reactions we saw earlier, the hydrogens appear as 2 places, so you got to think about that. But when you do that, you should get a balanced reaction for 2 NH3 plus 3 O2 plus 2 CH4 makes 2 HCN plus 6 waters. And again, again, don't be afraid to go back and balance this through as you see fit. The next one is also a little bit more challenging, all right, because you have the oxygen, the 3 oxygens in KClO3, potassium chloride, and oxygen going to water. And you've got to take into account all the different things. I would probably start by balancing the oxygens first and then move on from there. If you do that, you should end up with this reaction. KClO3 plus 6 HCl makes KCl plus 6 C, thanks for playing, plus 3 Cl2 plus 3 waters. And these are just a little bit more challenging, gives you something to think about. Most of the things we're going to look at, not only in this class, but in the Chem 200 class, will follow one of those 6 patterns of reaction we've seen. But this just gives you experience with some of the other types of reactions that are out there. Okay, that's it for problem set number 3. I hope this video has been helpful to you as you learn how to balance equations, types of reactions, things like that. If you do have further questions, reach out to me. mike.russell@mhcc.edu works really well. You can also talk to the LSC/Avid Center at Mount Hood. Good luck with your studying and have a wonderful day.